All right, we're on to our next topic, types of equilibrium. So what is equilibrium? Well, equilibrium is a state of balance. Well, let's look at equilibrium in more detail because there are some key features that we're going to need to talk about. Ready? First of all, to reach equilibrium, reactions must be reversible. That means it cannot be a completion reaction. A completion reaction is it finishes, it's done. There's no going backward. You can't uncook the egg, you can't unbake the cake, you can't unburn the log. Completion reactions. Some reactions are reversible. So, for example, you can refreeze water that's melted. That's reversible. Okay, so a reversible reaction has a forward reaction and it has a reverse reaction. But again, those are the types of reactions that can reach equilibrium. If it is a completion reaction, it cannot reach equilibrium. So again, a reversible reaction has a forward reaction and a reverse reaction. Okay, so here is an example with the formation of ammonia. It can go forward, producing ammonia, and it can go backward, breaking apart ammonia into its components. So this way would be synthesis, this way would be decomposition. And one way is always exothermic and one way is always endothermic. So if I'm telling you the forward reaction is exothermic, then you know that the reverse reaction is endothermic. Okay, so this is the production of ammonia. It has a forward reaction and a reverse reaction. So that means it can reach equilibrium. Okay, to reach equilibrium, a reaction must occur in a closed system. So as we normally might put a pot of water on the stove to boil, as the water is boiling and it evaporates, it is escaping unless we put a lid on it. So right here, this system is closed so that matter can't leave. Energy can, because we can have the flow of thermal energy from a warmer object to a colder object, but matter is not leaving. So if you put that pan of water on the stove to boil and put a lid on it, the amount of water is not going to go down because it's going to hit the top of the lid, condense, fall back down. Okay, as long as it is sealed as a closed system. We can have an isolated system, like think of the thermos. So that's going to try to keep the energy also inside. It's insulated. Okay, so if we have an open system, we have stuff escaping. Anything that's a gas can just leave. So that cannot reach equilibrium. In order to reach equilibrium, we need to close the system. Okay, so again, here up here is another illustration. In an open system, gases can enter, gases can leave, things could fall into the reaction. When we have a closed system, we put a lid on it. Okay, don't put a ring on it, put a lid on it. Put a lid on it, and it is a closed system. That can reach equilibrium. Chemical equilibrium is dynamic. What does that mean? Well, that doesn't mean that nothing's happening. So think about in a sports team. So you have, 6 players on the team. We can have substitutions going in, going out, but we're only going to have the correct number on the field at any given time. Okay. You can think about a dynamic equilibrium like an escalator, and you're going in the wrong direction. So the escalator is going down, but you're running up it. So the escalator's moving, you're moving, but you're not changing position. Okay, so it's dynamic. Here, this container is assuredly being filled with water, but at the same rate it's being filled, the water is emptying out. So it's not that nothing is happening. It's just that it is constant. So the forward reaction is still happening. The reverse reaction is still happening. Okay, but when we talk about rates later, we'll see the rates are equal. So as fast as this water is pouring in, it's coming out. As fast as this person is going up the stairs, the escalator is moving down. And just as these 3 players are coming off of the ice, 3 more are going on the ice. Dynamic equilibrium. The opposite of dynamic is static, meaning not changing. And that is not the situation in equilibrium. Equilibrium is dynamic. Okay, so this kind of leads into rate. The rate of the forward reaction has to equal the rate of the reverse reaction. So you can see as this reaction first starts, okay, I have no HI, and all of what I have is H2 and I2. And then slowly what happens is the forward reaction is continuing, the reverse reaction is continuing, and then eventually the rates are the same, equal. So that's equilibrium. So the rate of the forward reaction is the same as the rate of the reverse reaction. They're happening at the same rate, okay? The rates are equal. The rate of the forward reaction equals the rate of the reverse reaction. Now, concentrations are not equal, they are constant. So think about this, concentration, constant, concentration, constant. So what does that mean? I don't need to have an equal number of reactants and an equal number of products. But do you see what I have here? I have a constant amount of reactant and a constant amount of product, okay? So rates are equal, but concentrations are constant. And that's how I can tell when I reach equilibrium. So over here, this is not equilibrium. As soon as I reach equilibrium, the concentrations are constant. So again, not at equilibrium. Why? Because the concentrations are changing. And then over here, we are at equilibrium because the concentrations are constant. So again, two things. The rates are equal. So do you see forward rate, reverse rate, equal. Rates are equal. Concentrations are constant. Rates are equal. Concentrations are constant. So let's look at some types of equilibrium. So we can have phase equilibrium. So if the state of matter can change between two different phases, it can exist at a specific temperature, both phases. Okay, like for example, water has a melting point of 0 degrees Celsius, but that's also its freezing point. So at 0, water can freeze and ice can melt. Okay, so here's an example. So I can have both ice and water at 0 degrees Celsius. Now, this can technically not reach equilibrium. This can technically not reach equilibrium. Why? Because the container is open, right? So gases can escape. In order to make it reach equilibrium, I'd have to close it. But if I keep this at 0, that means the ice will be melting, the water will be freezing, and if they're occurring at the same rate, so just as fast as the water is freezing, the ice is melting. That would be equilibrium. So here's an example when we're talking about the liquid and gas phase, okay? So the rate of condensation is equal to the rate of evaporation. If I increase the temperature, so you can see this is a flame right here, the rates are still equal, it's just occurring faster. So the evaporation is occurring faster and the condensation is occurring similarly faster. So we can have a phase equilibrium between a liquid and a gas, between a solid and a liquid, between any states of matter that can coexist at the same temperature. But what will happen is as quickly as one is changing from, say, a liquid to a gas, we have the same amount that would be changing from a gas back to a liquid. So again, you can see rates, in order to be at equilibrium, have to be equal, right? Rates are equal. So at first we have evaporation and the condensation is speeding up. So we're not at equilibrium yet. As soon as we reach right here, we get to equilibrium because the rates are equal. So a state equilibrium, a state of matter equilibrium, is when we have two states of matter coexisting at the same temperature and the rates are equal. We can also have a solution equilibrium. And in the next unit, we're going to talk about solutions in greater detail. So we're going to revisit this. But a solution equilibrium can only happen in a saturated solution. But the important part to remember for this unit is that the rate of dissolving is equal to the rate of solidification or crystallization. So this is glucose, this is some sugar, illustrated here in this beaker. And some of it is dissolving and some of it is recrystallizing. Reversible, dissolving, there's the solid, the crystal. So some is going from solid to the aqueous state, which means it's being dissolved in water, and some is going from the aqueous state dissolved in water back to the solid, solidification or crystallization. So those rates are equal when we have a solution equilibrium. So which statement describes a reaction at equilibrium? Okay, so does equilibrium have anything to do with the number of moles having to be equal? No. Does it have to do with mass? No. Does it have to do with entropy? No. So hopefully it's this. It is. The rates have to be equal. So the rate of forming the products has to equal the rate of forming the reactants. The forward and the reverse reaction have to have equal rates. Okay. For a chemical system at equilibrium, the concentrations are, do you remember the word that goes with concentrations? Constant. Rates equal. Concentrations constant. So given this equation, which statement is true? Okay, so it talks about forward and reverse at equilibrium. So at equilibrium, do the forward and reverse processes stop? No. Does the forward happen faster? Does the reverse happen faster? Or do they happen at the same rate? Do you remember what does that mean to be at equilibrium? Same rate, equal rate, concentration constant. An open flask is half filled with water at 25 degrees Celsius. Phase equilibrium can be reached after. So what's one of the requirements for equilibrium? Do you remember? You have to close the system, put a lid on it, not a ring, put a lid on it. What type of equilibrium exists in a sealed flask if we have Br2L and Br2G at 298 Kelvin and 1 atmosphere? So do you remember what this means? That means a liquid. Remember what this means? That means a gas. Look, I have the same substance. So I have the same substance, two different states of matter in a sealed flask. What kind of equilibrium is that? Well, first, do you remember, is equilibrium dynamic or static? You should remember, hopefully, it's dynamic. So I know static is wrong. So what kind is it? Phase equilibrium, two different phases of the same substance. If it was a solution equilibrium, I'd need to see AQ. And equilibrium can be reached by both physical and chemical changes. And there you go. That's types of equilibrium. I hope that you learned something new today.